LSP as a unidirectional point-to-point link in the link state database, so that all the routers can compute paths using this LSP, so that even a router such as A can take advantage of the existence of this LSP in the network. So let's take a look at the summary so far. What have we seen so far? We've seen that we can load share traffic across paths with an equal cost. This was the fish diagram where we established the two LSPs, one over the upper path and one over the lower path, where CSPF naturally placed the two paths on distinct links because there was not enough bandwidth to satisfy both constraints. We've seen that we can enable definition of flexible forwarding policies. We saw that if we wanted to, we could force the traffic from A to take a particular set of links, and we could force it to always take the shortest path in the network. We've seen that we can route primary paths away from known bottlenecks or points of congestion. This is the example with the bottleneck link, where we saw that we moved the traffic away from the bottleneck link onto links where there was enough bandwidth. Finally, we've seen how we can control the path that BGP traffic, transit traffic, is taking inside the domain. And in the end, we've seen that we can traffic engineer just a portion of our network and mix paths determined by IP routing with paths determined by constraint-based routing. So let's take a look at a few other useful properties for traffic engineering. These are LSP priorities, automatic bandwidth adjustment, and path protection. So let's take a look at LSP priority and preemption. The idea is very simple. Some LSPs are more important than others and can kick out the less important ones if there is resource contention. Well, what does it mean? It means two things. First of all, if there's a failure in my network, and now all of a sudden I have a bunch of LSPs rerouting, and there's not enough resources for all of them, I can be sure that the important LSPs, the LSPs that carry the important traffic, are going to get these resources, and who cares what happens to the other ones. Secondly, what this ensures me is that my important LSPs are always going to establish along the most optimal path in the network. Regardless in the order in which the LSPs come up, the important ones are always going to take the shortest path. So one thing to bear in mind about is this, that all this preemption thing happens at the time that the path is computed and set up. It's not something that happens at forwarding time. Now, what does it mean an important LSP kicks out a less important one? Well, it means exactly that. It means like a very brutal thing. I have an important LSP coming along, there's resource contention with some non-important guy. Then the non-important guy is going to be kicked out of those links without any kind of advertisement towards the head end. So there is going to be traffic loss on the less important LSP. So there's a proposal in the IETF today to do some kind of gentler approach to this preemption, which is called soft preemption, and at least allow the less important guy to reroute before it's being kicked out in such a nasty way. Second nice feature is auto bandwidth. I've been talking about bandwidth constraints. I need to establish LSPs with bandwidth constraints. Well, what if I have no idea what the bandwidth constraints are? What if the bandwidth constraints change during the time of day? So the idea with auto bandwidth is I'm going to monitor the traffic rate on the LSP, and I'm going to resize the bandwidth on the LSP to match what is actually going on. So this may result in the LSP rerouting, but no worries, the traffic flowing down the LSP will not going to be affected. Finally, we'll talk about path protection. So there's a lot of noise in MPLS about traffic protection, and one of the simplest mechanisms for traffic protection is path protection. The idea is we're going to protect an LSP by having an additional LSP set up in parallel to it. The second LSP is a secondary standby, and is going to be set up and ready all the time to take over the traffic in the case of a failure. So the secondary standby is only used in the case of a failure, and the picture looks something like this. Let's say that I have a primary LSP between A and C taking the path ABC, and I have a secondary LSP taking some other distinct path in the network with the same bandwidth reservation as the primary. So the advantage is quite clear. I have precise control over where the traffic goes in the case of a failure. I know exactly where it goes. More than that, I have reserved enough bandwidth on the secondary standby path so I can be really sure that there's going to be no problems when my primary fails. The second advantage is that the secondary standby is taking a diverse path in the network. That means I have very little chance that both the primary and the secondary are going to fail. The disadvantages are also quite obvious. This is a quite wasteful approach to doing a backup, because I'm reserving resources for the backup, but most of the time these resources are not used. The second thing is that we're going to build this secondary, we're going to build one secondary for every path that we protect. So from the point of view of scaling, this doesn't scale very nicely. And thirdly, and most importantly, the secondary standby is only going to kick in when the head end finds out about the failure. Now, if the failure happens somewhere in the middle of the LSP, it may take a while until the head end figures out there was a failure in the path. So to take a step back, let's see the other applications that we've seen so far. We've seen that we can use priority and preemption to ensure that the important traffic always gets the optimal path and always gets resources. We've seen the feature of automatic bandwidth, which allows bandwidth adjustment regardless of what the rate of the traffic actually is. And finally, we've seen path protection, which gives us precise control over how a path is rerouted in the case of failure. Are there questions so far? Okay. So let's talk about fast reroute. So when I say fast reroute, what I'm going to talk about is the general concept of fast reroute and not the Juniper feature with that same name. Okay? So as with traffic engineering, the problem of fast reroute is not a new problem. What happens is that if there is a failure in a network, it will take a while until the failure will be detected and until everybody else will find out about the failure and recompute their forwarding path. So in the meantime, the traffic is going to get lost. So the goal is to minimize the time that it takes, the time during which there is packet loss during routing transient. And there are two factors at play here. First is the time to detect the failure, and it's going to be the time it takes to detect a link down event, or the time it takes to detect a link node event. And second is the time that it takes to distribute the information about the failure and recompute forwarding tables. So the problem with IP routing protocols is that they are distributed in nature. So it requires that all the routers in the network converge to a consistent view of the routing information before they can ensure me that there will be no black holing of traffic and no looping of traffic. So in a large network, there may be convergence time on the order of a few seconds. So what's the idea behind fast reroute? The idea is very simple. The idea is, well, let's forget about convergence. Let's just have like a small goal in mind, a very, very modest goal. All that I want to do is take the traffic from one end of the failed link and shepherd it around it on some alternate path to the other end of the failed link. And I will patch, in this way, I will patch the traffic on an alternate path and prevent packet loss. So this approach is a very, very, very local approach. It protects a link or a node in the network. If you think back of the path protection has like these big aspirations. It wants to protect the entire path. What fast reroute does is like, I want to protect just a particular resource in the network, a link or a node. And let's talk about link protection only because it's conceptually easier to understand. So what does it look like? It looks like this. We have a link AB, and we have a protection path around the link AB that's taking some other path in the network. It's going through the path ACB. So when the link AB fails, what we're going to do is we're going to take the traffic and forward it along the path ACB around the failed link. We will still have some traffic loss because we need to detect the failure and then we need to switch the traffic over. But we will have much less traffic loss than if we waited for the whole network to converge. Well, so can we take this approach with IP? Let's take a look at the following example. We have the link AB is the link that we want to protect. And we have traffic traversing this link. And node A knows that traffic destined to B should go over the link AB. And node A also knows that there's a protection path going along ACDB. From C's point of view, however, because of the way the metrics are set up in this example, he thinks, okay, the best path to forward traffic towards B is along through node A along the link CA. So let's see what happens now when the link breaks. When the link breaks, A detects the link going down and starts sending traffic to B, traffic destined to B along the protection path. So it sends the traffic to C. C gets this traffic and starts making his own forwarding decision. He says, oh, okay, this is traffic for B. Let me forward it along the best path to B and forward it right back to A. So the traffic is going to loop between these two guys until such time as C is going to realize that, oh, the link AB went down and take some other measure. So what's the problem? The problem is that C was making an independent decision on how to do the forwarding on the protection path. So if this is what is foiling our scheme, then we can remember that in MPLS we have decoupling of the forwarding decision from the destination of the packet. So let's try to do the same scheme with MPLS. So the idea with MPLS is we're going to construct these protection LSPs around the point of failure, and then we're going to push the traffic that was passing along the failed link. We're going to push it on the protection LSP. So let's look at the following example. We have the LSP XY, and this LSP is crossing the link AB. The link AB is the weakest link, and we want to protect against failure of the link AB. So what we're going to do, we're going to construct a protection LSP, a pink LSP, going around the link AB through the nodes ACDB. So let's see what the label distribution looks like. So we have the blue LSP, the upper LSP is the original LSP that traverses the link. Label distribution happens as follows. From the tail end, Y is advertising a POP label to B. B is advertising label 100 and installing forwarding state of POP 100. A is advertising a label 101 and installing forwarding state of swap 101 to 100. And finally, X is going to install forwarding state of push 101. Similarly, we're going to have label distribution on the pink LSP, the protection LSP below. And I'm going to use labels in the range of 200 there just for the example. So let's see how traffic is forwarding along the blue LSP when there is no failure. So traffic arrives at X. X is pushing label 101 onto the packet. A labeled packet with label 101 arrives at A. A swaps label 101 to label 100 and sends it over to B. Finally, B receives a packet with label 100, pops that label and sends the packet to Y. So what needs to happen if I want to use this same scheme and push the traffic on the protection LSP? If I could just trick this traffic to take the protection LSP and arrive at node B with the same label as if it was coming on the link AB, then B wouldn't know the difference and I would just forward as normally. So what do I need to make happen in order to trick B and make sure that the traffic arrives to B on the protection LSP with the same label? What I need to do is at node A, I will swap the label 101 to label 100, as I was doing before, because I want label 100 to show up on my packet at some point later in the path. But I will also push another label, the label 201 that belongs to the protection LSP, and then I'm going to push the packet out of the interface AC. So let's see what happens in the case of a link failure. Traffic arrives from node X with label 101 as before. Now A knows that the link AB failed. So what A is going to do is going to swap label 101 to label 100 and push label 201 and send it on the link AC. Now the packet has a two-label stack. The forwarding on the pink LSP, on the protection path, is going to happen based on the top label only. So the label 201 is going to be swapped to label 200. At node D, label 200 is going to be popped. And here we have the packet arriving at B with the same label as if it had arrived over the failed link. So B is going to take this traffic, pop the label, and send it to Y. So what's the difference between this example and the IP example that we saw before? Why is this working in this case and it wasn't working then? The difference is that once I put the traffic on the protection LSP in this case, the traffic of this, the fate of this traffic is sealed. The packet is going to have to come out, to pop out at the end of the protection LSP, and there is nobody in the path who's going to make any kind of independent decision of what to do with it. So let's take a step back and look at the same example and say, well, what if there was another LSP, a green LSP, let's say again between X and Y, that was also crossing the link AB? Could I use the same protection LSP to protect the traffic from the green LSP? The answer is yes. There is nothing in this model to prevent me from doing so. All that I need to do is to install the appropriate forwarding state at A. From the pink LSP's point of view, he doesn't care how many different LSPs are encapsulated. All that he does is he does forwarding based on the top labels. So let's see what we've seen so far. So far we've seen the example of a link protection. We were protecting the link AB. So first of all, please note that the protection LSP was set up ahead of time. In our example, we showed that the distribution of labels for the protection LSP was happening at the same time that the distribution of labels for the primary LSP, for the blue LSP. And this is pretty much what needs to be happening in order for this to be meaningful. Because if I was to wait until the failure was happening in order to start calculating the protection path and signaling the protection path, all this scheme would be quite meaningless. Second, traffic loss is still going to occur. Traffic loss still occurs because there is a delay until A figures out that the link went down and then switches the traffic to the protection LSP. Now the question is, so what is the amount of time that we're going to lose traffic? So for example, in the Juniper implementation of fast reroute, in the normal day-to-day cases, it can be done in 50 milliseconds, including the detection time. So what you can see is that with this kind of scheme, you can really achieve very, very, very short amounts of traffic loss. Thirdly, the intention is to use the protection LSP for a short time until a new path will be recomputed. Clearly, this protection path is not an optimal path in the network. More than that, did I say anything about bandwidth protection along that path? I didn't say anything. I hammered for half an hour about these bandwidth constraints before, but now I have the protection path. I didn't say anything about bandwidth protection on that path. Worse than that, I said several LSPs can use it if they're crossing the same link. So clearly, I can't be relying on this protection path for too long. So in the case of link protection, the protection LSP protects a link. The protection LSP is signaled around the protected link from the node upstream to the node downstream, and it's done so ahead of time. And traffic from one LSP or from many LSPs can be carried over it. And this has different scaling properties and different trade-offs. So in the example that we've seen, several LSPs could share the protection path. So this is very nice from a scaling point of view. On the other hand, I can't guarantee the bandwidth on that. There is also a one-to-one scheme where the protection LSP only permits protecting one particular path. So the feature that is called Juniper Fast Reroute is a one-to-one protection, which also optionally offers bandwidth protection as well on the protection path. While the feature that is called linked node protection is a one-to-many scheme, which gives you the advantages of scaling, but does not offer any kind of bandwidth protection. Finally, when we're talking about link protection and about fast reroute, we're talking about RSVP really. It's RSVP LSPs. All the standards that are defined today are defined for RSVP. But if you take a step back and think of the concept of taking the traffic and putting it on the protection path, you can see that this concept can be extended to all kinds of other things. And there is all kind of work in that direction. So let's take the summary of fast reroute. So what we got now is that traffic loss has become a function of the link failure detection time rather than being a function of the head-end rerouting or of the network converging. Secondly, the protection LSP is intended for a very short amount of time after the failure. So it's only intended to be some kind of temporary patching until the head-end can recompute the path along some optimal path in the network. And finally, you can choose to protect just a few of your resources in the network. So you can choose to protect as many or as few of the resources that you want. Now the question that you may ask is, well, can I use this kind of scheme in conjunction with path protection? And the answer is yes, of course. There is, in fact, when you do so, you achieve the best of both worlds, because you can use the fast reroute scheme in order to patch the traffic quickly until the head-end finds out about the failure, and then switch to the secondary standby, which gives you precise control over where your traffic is flowing. Are there questions so far? Yes, please.
When do you set up that protection LSP? Like, is it generated dynamically somewhere?
Yeah, it's generated. So the thing is, you need to configure in several places in your config, but it will happen dynamically. It's going to be generated dynamically. So you have to specify which link you want to protect or which resource you want to protect. But from that point on, it's going to happen magically.
So you tell it which link to protect?
Yeah.
Comes up with. Okay.
The protection time we're talking about milliseconds or so, that time would be dependent upon the transport.
Yes, of course. Of course. So the question was, well, the times that I quoted is also the 50 milliseconds or so is going to be also dependent on the detection time of the failure detection time. So of course, if the transport doesn't support some kind of quick detection, then I'm hosed pretty much. Any other questions? Okay, then we can carry on to the next section, which is VPNs. So VPNs is also not a new concept. VPNs existed long before MPLS ever was around. So what we're going to see now is how we can use MPLS to improve the scalability of VPNs. So the reason why VPNs existed long before MPLS ever came about is that the problem that VPNs are solving is a very old problem. Basically what we have is a company that has several sites in several separate geographic locations, and it wants to achieve connectivity between them. But it doesn't want to actually buy the links to connect the sites, so it wants to do so over some kind of shared infrastructure, some kind of a provider's infrastructure. On the other hand, it wants to achieve the same guarantees as if it was a private network. First, I don't want to see anybody else's traffic in my network, and I don't want my traffic, God forbid, to go into somebody else's network. And second, I want to be able to use any kind of addressing scheme I want internally. So what does it look like? The picture looks like this. We have a few different sites, and they're not interconnected between them. And what we want to do is we want to achieve connectivity between them across the provider's networks. So the first models of VPNs were the overlay models, where we would actually do physically what I just showed conceptually in the picture before. So what we would do is connect all these sites with point-to-point links, frame relay circuits, ATM circuits, whatever. So the customer routers would peer with other customer routers at the end of these links, and the customer would run his own routing. And from the provider's point of view, he only provides the links. But the provider needs to give these virtual backbones for all the customers. At some point, it becomes cumbersome to start managing like all these virtual networks on top of the provider's networks. So the goal of BGP MPLS VPNs is to solve the scaling issues with the previous model. The goal is to support thousands of VPNs and VPNs with hundreds of sites per VPN and with overlapping address space, so that there is no requirement on the customer to use any particular addressing. This model is a peer model. The customer routers peer with the provider's routers. So let's take a look at the terminology for this model. So we have 3 customer sites, and on each customer side there is a customer edge router which connects to a router on the provider side. The customer edge router is called the CE router, and the router on the provider edge is called the PE router. Now all the other routers in the provider's network are called the P routers. So what we have is we have CE routers peering with PE routers, and they don't peer with other CE routers. So the properties of the model are that we have CE routers peering with other PE routers, but not with other CE routers. And when adding or deleting a new site, all that it means is we need to configure the PE router connected to the site. Finally, we're going to see at the end of this section today that the PE router only needs to maintain routes for VPNs whose sites are directly connected. So rather than presenting the entire solution, I'm going to try to build it here step by step logically, and then the requirements are going to become quite apparent. So let's take a step back and see what were our goals. Our goals were to give the same privacy guarantees as a private network. That means I don't want the traffic from my VPN to go in somebody else's network, and similarly, I don't want to see somebody else's traffic in my network. So we're going to see how this can be achieved with separation of forwarding. Secondly, what was the the driver for all this. I wanted to achieve connectivity between my sites. So we're going to see how we achieve connectivity by doing distribution of routing information. Thirdly, we wanted to have overlapping to allow private address spaces for each one of the VPNs. And we're going to see how this is achieved with a new address type. And finally, we wanted to forward traffic among these different sites. So we're going to see how this is achieved with MPLS. So let's start with our first goal. The first goal was to achieve the privacy of the traffic. So we don't want to mix traffic from one VPN with traffic from another VPN. So what we want to do is want to split the forwarding information. If I had a PE router connected to CEs from several VPNs, if we put all the forwarding state in a single table, then it would be possible to forward packets from one VPN to another. So this is solved by having multiple forwarding tables, and each table is associated with a particular site. So packets from a customer are associated with a particular table based on the interface on which they arrived. And the contents of these forwarding tables are routes received from the CE and also routes received from the remote PEs. So let's see how routing information is distributed in this model. So what's the idea? We have the CE advertising routes to its local PE with some routing protocol, or even with static routing. So now the local PE is going to take these routes, mark them with some extended community, and advertise them in BGP. This extended community is actually what is called the route target in VPNs. So now BGP is going to take and advertise these routes with the route target to all the remote PEs. And the remote PEs which receive these routes, they filter them out based on the community and advertise them back to the CEs. So let's see an example of what's going on. Let's say that we have two customer sites, site 1 and site 2. And site 1 has routes in the 10.1/16 range, and site 2 has routes in the 10.2/16 range. So now CE1 is going to advertise route 10.1/16 to the PE that's connected to it. The PE is going to attach a community, let's say community green, to it, and advertise it to all the other PEs. So now in the BGP advertisements, we have 10.1/16 community green, 10.2/16 community green, which would seem to be all right, except if we had two more sites from a different customer, from customer gray, which was using the same address space, the overlapping address space, we would have a problem, because we would attempt to advertise the same prefixes with different communities. So the model so far that we've seen so far, we cannot, we have a problem. We have to have distinct address spaces for each one of the customers. So in order to solve this, we use a new address type. So the goal is to turn these non-unique addresses into unique addresses. And we do this by concatenating an IP address with an 8-byte unique identifier, which is called the route distinguisher. So this new address type, which is called the VPN IP address, is advertised in a special address family by BGP and is used only inside the provider's network and used only in the control plane. There is no forwarding based on these special addresses. The translation between a normal IP address and the VPN IP address happens on the PE. The customer doesn't know anything about these addresses and never cares about them. And the most important thing that one needs to keep in mind is that these route distinguishers are not used at all for route filtering. We use the communities, the route targets, to do that. The route distinguishers are only used in order to enable use of overlapping address space. So let's look at the same example as before, and let's see how the use of route distinguishers fix the problem. So we have the green customer and the gray customer, and they're using the same address space, except now we're attaching the route distinguisher to the address. So inside the BGP advertisement, we have distinct addresses being advertised with the respective communities, and there is no problem. So now we can use overlapping address spaces, but we exchanged one problem for another, because now I have no idea how to forward based on these kind of weird addresses. So as we've seen before, what MPLS does, it decouples the forwarding decision from the destination address. So let's see how we can use MPLS in order to do forwarding in this case. So let's take a look at the example here. So we have a customer in VPN Green at site 1 who wants to send traffic to some destination in site 2. So let's say he wants to send traffic to 10.2.1.1 in site 2. So the traffic arrives from CE1 to P1, and based on the interface over which this traffic arrives, P1 knows that this traffic belongs to VPN Green, so it goes ahead and looks inside the forwarding table for VPN Green. It says, oh, okay, this is an address in the 10.2/16 range. I know that that advertisement came from PE2. Let me forward this traffic to PE2. Now, if there is a label switched path between PE1 and PE2, I'm going to just take the packet, encapsulate it into MPLS, put the appropriate label of this label switched path, and send it to PE2, and then PE2 should be able to figure out that this traffic belongs to VPN Green and send it to the right site. And this seems really nice, except if the picture was a little bit different. What would happen if now I had two other sites from some other customer, customer Gray, connected to the same PEs? Let's see what would happen now. I would take the packet. The packet would arrive from CE1 to PE1 over the interface that's connected to VPN Green. PE1 would know that it needs to look in the green forwarding table to forward this packet, and it would correctly decide it needs to send it to PE2. The packet would travel across the label switch path to PE2 and arrive at PE2. And PE2, what does it do with it now? It has no idea. Does the traffic belong to VPN Green or to VPN Gray? The problem is that the traffic is not marked in any way. The traffic is not identified in any way as belonging to a particular VPN. In the routing plane, we had these communities that would identify which VPN the route advertisements belong to. In the forwarding plane, we don't have the equivalent. So the idea is like, okay, why don't we use a label in order to identify the VPN? Let's see what would happen if we had a label. But first, let's say how the label is advertised. So the VPN label is going to be distributed by BGP along with the VPN IP address. At the same time that the VPN IP address is advertised, a label is going to be advertised with it. And now the traffic is going to carry two labels, the VPN label and the LSP label. And the remote P is going to make the forwarding decision based on the VPN label. So let's take a look at the same example using VPN labels. So customer Green is sending traffic to 10.2.1.1. P1 already knows to look in the forwarding table, and it knows it needs to send the traffic to P2. But it also knows that it needs to attach a VPN Green label to this traffic. So now the traffic is going to travel along in the network with a two-label stack. The inner label, the bottom label, is the VPN Green label that identifies this traffic as belonging to VPN Green. The outermost label is the label of the label switch path between P1 and P2. So when a packet is going along the path this way, the forwarding is going to happen based only based on the uppermost label. So finally, the packet is going to arrive at P2, with the VPN green label on the top, and PE2 has no trouble identifying that this is a packet destined for VPN green and send it out on the correct interface. Now what if we were receiving a packet on VPN gray? PE1 would figure out that this packet belongs to VPN gray based on the interface on which the packet arrived, would put a two-label stack on the packet, a VPN gray label, and then the label that's appropriate for the label switch path between PE1 and PE2. The packet would arrive at PE2 with a VPN gray label, and PE2 would have no trouble sending it to the correct CE3 in VPN gray. So another interesting thing that we note in this picture is that look at the two P routers in the middle of the network here. What do these two P routers need to do? They only need to be able to switch packets based on labels. They don't need to know anything about VPN IP addresses. They don't need to know anything about any of the VPN routes in this network. So this is a very important scaling property of this model. The P routers don't have to carry all the VPN routes in the network. Think about it. If we had a single element in the network that would have to carry all the VPN routes from all the VPNs in the network, this would be the scaling bottleneck of the system. Well, the P routers don't have to know anything. We're going to see later that the P routers need to carry some VPN routes naturally, but only for those VPNs for which they have sites attached. So what we're going to see is that no single element in the network needs to carry all the VPN routes in the system. So let's take this summary so far. The P routers don't need to maintain VPN routes at all. They only need to maintain routes to other P and P routers. The P routers need to maintain VPN routes, but only for those VPNs that have sites attached to them. And finally, VPNs can have overlapping address spaces. Yes? Through a route reflector, yes. So the question was, well, you have to have a full mesh of BGP connections between the PE routers, and that is correct, but you can use route reflectors to do that. Any other questions? Okay. So now let's say, so can I take this same concept and expand it from layer 3 to layer 2? There's nothing in the model that I showed so far that would prevent me from doing it. So in the L3 VPN model, what I had was that I had the remote Ps advertise IP addresses and VPN labels. What I can have now happen is I can have the remote Ps advertise layer 2 information and VPN labels. And what is going to be the end result of this is that I can emulate a layer 2 point-to-point connection over the MPLS network. And I can carry PDUs of layer 2 protocols over MPLS. So let's see what this looks like. Let's take a look at an example with frame relay. So let's say that I have two sites, site 1 and site 2. And there's two frame relay connections, a black one and a red one. So what PE2 is going to advertise is going to advertise for each one of these two connections a VPN label and information, L2 information that will allow PE1 to map the traffic correctly to PE2. So let's see what happens when an L2 PDU is sent from CE1 to PE1. So PE1 is going to, based on the DLCI and interface, PE1 is going to find out which one is the VPN label and which one is the PE to which we need to send this traffic. And it's going to put the two label stack, just like in the layer 3 example that we've seen before. So we're going to put a VPN label, a black VPN label, and put it on the LSP between PE1 and PE2. the packet is going to arrive at PE2. The VPN, based on the VPN label, the correct connection is going to be identified. The packet is going to be forwarded again as an L2PDU to the other side. Similarly, if we were sending traffic on the red connection, the traffic would arrive at PE1. PE1 would identify the correct VPN label to put on top of this traffic, and then would send it on the LSP towards PE2 with a 2-label stack. The traffic would arrive at PE2 with a VPN label, and based on the VPN label, it would be sent on the correct connection. So what I haven't said is, how is this layer 2 information advertised? So there are two main, the two protocols available today. One is the L2VPN compeller draft, which uses BGP in order to advertise this layer 2 information in the network. So similarly to what we've seen in the layer 3 example, we use a new address family and put in there all the information that we need in order to do this. The second draft is the Martini drafts that use extensions to LDP in order to achieve the same thing. So the LDP protocol is extended, and rather than just advertising labels for IP addresses, it advertises labels for connection. So the Martini drafts are now called the PWE drafts. It's the PEW3 working group in the ITF. So other questions so far? Okay, so we've reached the last part of the presentation, which is a protocol comparison between LDP and RSVP. So this is like not a discussion on which protocol is better. It's rather a discussion of, well, which protocol is applicable to which kind of environment. So before we start doing that, let's make a short revision of the two protocols. Let's take a look at LDP first. So the most important thing that one needs to remember about LDP is that LDP is not a routing protocol. LDP relies on other routing protocols to make the forwarding decisions and to do the loop prevention and everything else. LDP itself cannot do anything without relying on another routing protocol. The one thing that derives from this is that the LSPs that are established with LDP usually follow the IGP shortest path in the network. The label distribution is initiated from the endpoint, and there is no concept of a head end requesting the establishment of an LSP to the endpoint. And finally, all our label exchanges are label exchanges between LDP neighbors. The label exchanges are done with TCP, so they are reliable and they're incremental updates. RSVP, on the other hand, is an extension of the resource reservation protocol. It's got soft states, it requires periodic refreshes, and it creates point-to-point tunnels initiated at the head end. So labels are only distributed along these paths. It supports explicit paths, so we can set up LSPs along paths computed with CSPF, so we can take into account bandwidth allocation, and we can do constrained bit routing and traffic engineering stuff. And very, very powerful for RSVP. RSVP supports fast restoration in case of failures. So let's compare the two. So there are three main fields of comparison. What's the ease of configuration? So for RSVP, we need to configure the head end, and we need at the head end to say, well, who's the tail end of the LSP? Now, if I want to maintain a full mesh of LSPs, when I want to add a new LSP to the network, I need to now go and configure all the reverse path LSPs from all the other nodes. So it's quite a considerable configuration burden. LDP, on the other hand, if I want to add a new node in the network, all I do, I put it in, I enable the protocol, it will automatically discover the neighbors, it will automatically distribute labels, and it will just work, well, hopefully. Secondly, from the point of view of state maintenance, I don't want to get into the discussion of soft state versus non-soft state, but just think about it this way. I have to maintain either relationship with a constant number of neighbors, or I have to maintain state for some number of tunnels, n number of tunnels, where n is going to grow every time I add a new node in the network. So there is a cost there too. Finally, there is the issue of LDP tracking the IGP state to determine forwarding state. What this means is that we have now two protocols going in tandem. So when you have two protocols that need to go hand in hand, there is always going to be race conditions. And what is important to understand here is that this is not an implementation issue. This is a protocol issue. Whenever you have like a protocol defined in a way where he has to go and work in conjunction with another protocol, there's going to be some racing going on. So finally, let's look at the applicability table. Both LDP and RSVP do label distribution, and we can use both of them in a VPN environment to establish the path between the PEs. Now, only RSVP has traffic engineering capabilities, and only RSVP has traffic protection. And yes, CRLDP was defined with traffic engineering capabilities in mind, but I'm completely ignoring CRLDP in this discussion since CRLDP was abandoned in the IETF as a standard. So, questions so far? Okay. So finally, to conclude is, there are many more topics in MPLS that we haven't touched on. There's RSVP soft preemption, there's DivServTE, which is a new topic on which there's now a lot of activity in the IETF going on in the TE working group. There's the question of node protection, which I avoided completely during the discussion of fast reroute. Very important, there's a bunch of drafts on graceful restart, which allows you to quickly recover after a failure of the control plane. There's a very large amount of work going on for ways to detect failures of LSPs. LSP ping is one of those mechanisms. There's VCCV in the PE working group and other initiatives, BFD for MPLS and so on. VPNs, we barely scratched the surface. And VPLS, which is the same concept as, which allows you to establish a virtual private LAN service, is a very new thing and very exciting that's only now getting acceleration. So this is all I had for today. Thank you very much. If there are any questions, I'll be happy to answer. Thank you.